We present our work on knowledge-enabled motion generation for complex manipulation tasks. In this work, we have shown that using only a few demonstrations of a task and associated by a knowledge base, it is possible to generate motion plan for the task on functionally similar objects. Consider the situation where we have a Cheez-It box, a bowl, a large pan, and a spoon on the table, and the robot is to perform the pouring task from the Cheez-It box. The Cheez-It box being directly manipulated by the robot is considered as a primary object for this task, highlighted in green, whereas the bowl and the pan are the passive objects, highlighted in blue. More than one instance of the pouring task is possible with these objects. For example, the robot can pour from the Cheez-It box into the red bowl or into the large pan. To be able to perform this task, the robot requires a demonstration of the task, possibly with a different object. In this case, it has one such demo with a soup can into a bowl. Using the labels of the object lying on the table and their mutual relationship in the knowledge base, we can infer that pouring from the Cheez-It box is possible using the demo of the soup can, as they both are functionally similar. Now the question is whether it can use the soup can demonstration directly on the Cheez-It box. Although they both belong to the movable containers class in the knowledge base, they greatly vary in shape and size. A related work addresses the problem of motion plan generation for the same objects as used in the demonstration, but with different poses. The motion is computed with respect to the object reference frames and captures the task-related constraints using the screw geometry of motion. Unless we take the geometries of the objects into consideration, direct application of that work will not work in our case. As you can see, direct application of the soup can demonstration on the Cheez-It box failed, as the content was poured outside of the bowl. Also, for objects like Cheez-It box, it is desirable to pour from the smaller edge of the opening. To overcome this problem, we take object geometries into account by introducing a new reference frame C. For the objects used in the demonstration, we compute the pose of the C reference frames attached to their openings by considering the geometries of the object like height, dimensions of the opening, etc. Similarly, for the objects used in the task instance, we assign the C reference frames at their respective openings. To summarize, we compute the C reference frames for the objects used in the demonstration and capture the motion of the C frame associated with the primary object soup can with respect to the C frame of the passive object bowl. Then, for a new task instance, the captured motion from the demonstration is used to compute the motion of the C reference frame of the primary object Cheez-It box with respect to the passive object bowl. Guided by this newly introduced C frame and the information from the knowledge base, the robot can now perform the task of pouring from a Cheez-It box using the demonstration of pouring from a soup can. Our approach can be applied to many functionally similar objects like a Cheez-It box, a large can, etc. It can also accommodate changes in the poses of the primary and passive objects. This can also be extended to a different arm as compared to the one used in the demonstration. And it is general enough to be applied to other complex manipulation tasks such as scooping. And execute the trials with the left arm as well as with the right arm.